So in this video we're going to go over finding the basis of a two-dimensional subspace. So it says consider the subset of R3, so the vector space R3, that consists of vectors that have the form A minus B, and B. So we know this is a subset of R3 because it's a 1, 2, 3 component vector. And we want to show that the vectors of this form actually form a subspace. We only want to look for a basis of a subspace. So first we need to identify that we are actually working with the subspace. And then once we find the basis, we want to determine the dimension and hopefully remember to interpret the geometry of that subspace. So to show, remember when we have a subset to show of something that's already a vector space, to show that it is itself a vector space, in other words a subspace, we only need to show closure. So we show closure under scalar multiplication and closure under vector addition. So to show closure under scalar multiplication, we'll grab a scalar c and we'll multiply it by a vector that has this form. So I'm going to use c comma c minus d comma d. So there's a vector that has the form a minus b, b. And we then just, well, we don't want to use c. That would be dumb because I'm using c for my scalar. So it's going to be d. And then we'll do d minus e and then e. So still a vector of the correct form. We don't want to use c to represent a vector component if I'm using c to represent the scalar. So when we distribute c into the vector, we get c times d, comma, and then we get c times d minus e, comma, we get e. And then we can clean this up a little bit. This is going to be cd. Distribute the c into the parentheses. So we get comma cd minus ce, comma ce by distribution. And then this is going to equal, if we look at this is a vector of the form a minus b, b, where a is equal to c times d, so a is equal to c times d, and b is equal to c times e. So scalar multiplication is closed. When we multiply by the scalar c, we get a vector that still has the correct form. And now we need to show closure as well under vector addition. So to show closure under vector addition, get two vectors of the correct form. So I'm going to get c comma c minus d comma d. There's one vector of the form a minus b, b. And then we're going to add it to another vector of the same form. So we'll use e minus f, f. And then we just do the addition. So we get c plus e in the first component position, c plus e. We get c minus d plus e minus f, comma, and then we get d plus f. And then we want to work on cleaning this up just a hair. So in the first component position I have c plus e, comma. We're going to regroup and recombine these using the commutative and associative properties of addition. So we wind up here getting a c plus e, and then we get minus, by factoring the minus out of the minus d minus f, we get minus d plus f, and then here we have a d plus f. So this is actually a vector of the correct form. This has the form a minus b, b, where a is equal to the c plus e. So a shows up here, and b is equal to d plus f. So the b is showing up here and here in the d plus f position. So we see that we're closed under vector addition because when we add two vectors of the form dictated by the subset, we wind up with another vector that has the form that's dictated by the subset. So once we've shown closure, then we know that we have a subspace. So we're all excited about that. We have a subspace. Yippee. So what remains is to find a basis for the subspace. So what we do to do that, we go a A minus B, B. We want to pull this apart as a sum of two vectors that add up to this. So I'm going to go A, comma, 0 plus, so here's my two A's, and then in the first position there is no B, so I'm going to go plus 0, comma, and then minus B, comma, B. And if we add these together, we'll get back what we started with. A plus 0 is A plus minus B is A minus B, and 0 plus B is B. And then we want to recognize that we can then factor the A out of the first one, which will leave us with 1, 1, 0, plus, and B can be factored out of this vector, B times 0, negative 1, 1. And now we see that every vector of this form can be written as a linear combination, because A and B are just scalars, they're just real numbers. Every vector of this form can be written as a linear combination of these two vectors. So the basis for our subspace is the vectors 1, 1, 0 and 0, negative 1, 1. There's our basis. And this basis has two vectors in it. So if we're interpreting this geometrically, what we would do, because the vectors aren't parallel, the one vector isn't a scalar multiple of the other, so when we put them toe to toe, they would form a plane. So two vectors geometrically describe an entire plane. So that's the geometric interpretation of this basis. We could try to verify that clearly these two vectors span the space. Clearly they span the space. But remember, they need to also be linearly independent if they're a basis. So, it would make some sense to verify that they're linearly independent. I tend to ignore that because I know that they are. But, if we were to formally verify that they were linearly independent, we could go, hey, let's do a scalar times 1, 1, 0, plus a second scalar times the vector 0, negative 1, 1. And this needs to, we set this equal to the 0 vector. This is how we test for linear independence. And then we say R is the only solution C sub 1 equals C sub 2 equals 0. Is the only way we get a solution if we is for us to use the trivial solution. So we don't want non-trivial solutions. So if we did this, we would get C times 1 is C sub 1 plus C sub 2 times 0 is 0. And so this means that C sub 1 would need to equal 0. If we look at the third component, the only way we're going to get this to work out, we get C sub 1 times 0 is is 0, plus C sub 2 times 1 is C sub 2, and that has to equal 0. So the only way we're going to get, we can see from those two components, the only way we're going to get the 0 vector is for C sub 1 to equal C sub 2 to equal 0. So they're definitely linearly independent vectors. And when you have only two vectors, you can eyeball it and tell they're linearly independent just by mentally multiplying them by a scalar. If you can't multiply this single vector times a scalar and get this one, and this only works when you have two vectors, it works if there's more than two vectors, but if there's only two vectors, then this is the only thing you need to do to check, is what I'm trying to say. But you look at this vector and this one, you say, is it possible to multiply this vector by a non-zero scalar and have it scale to this vector? And it isn't, because nothing besides 0, when you multiply it by a 1, will give you a 0. So that's kind of another way to mentally verify that we have a linearly independent set. So clearly we span. This proves that we span the set of vectors that look like this. This proves that they're a linearly independent set, which means that they are definitely a basis for the subspace.